Okay, so when we talk about a cell, and if you were to buy a cell from the shop, right? Okay, this maybe is a 1.5 volt double A cell. If you were to cut it open, you'll notice got electrolyte solution. So what it means is when the electrons are passing through the cell, remember the chemical energy is converted to electrical energy and passed to the cell, passed to the electrons. But these electrons will also collide with the ions in the cell. And when it collides with the ions in the cell, it will cause it to lose energy as heat. So that is the source of internal resistance, which you can't really avoid. But when this internal resistance, right, we cannot measure it. That means you cannot connect an ohm meter and measure it. Because how the ohm meter works is, it passes a small current through a resistor, and from the current that flows, it calculates the resistance. But since your cell already can generate a current, so it will mess up with the current from your ohm meter, so you cannot calculate the resistance accurately. So the only way to know what is your internal resistance is to calculate it. So how to calculate? There are a few steps to follow. So the first thing is, what you should do is, now let's say your cell, okay, has an internal resistance. So we'll draw the internal resistance R, small r, in the cell next to it. So you just draw the internal resistance next to it. Now you treat it as any other resistor. So we will connect your cell. So let's say this is my cell. I will connect it straight away to a voltmeter. Now when you connect your cell straight away to the voltmeter, what will your voltmeter show you? The voltmeter will show you the reading of the EMF. So I put in VV. So what it means by VV? It means the PD across the voltmeter is equals to the EMF Actually, it's almost equal to So what do you mean by PD of the voltmeter is equals to the EMF? Now the voltmeter is actually a high resistance resistor, but it is able to tell you the voltage. So that's the difference between a voltmeter and a resistor. A voltmeter is smart enough to tell you its own voltage, but it's just another high resistance resistor. Okay, so now it will give you the EMF if you connect the voltmeter straight away to the cell. Why? Let me tell you why. Because the voltmeter, when you say it's an ideal voltmeter is resistance approaches infinite. So when the resistance of the circuit is so high, can the current flow? Because your resistance approaches infinite, your current in the circuit approaches zero, right? So the PD across your internal resistance is I times R. But since the current here is almost zero, so the voltage across your internal resistance is also almost zero. So according to Kirchhoff's second law, or before we learn Kirchhoff's second law, so we talk about conservation of energy, where your net EMF or your total EMF equals total PD. So that means by right, the EMF here E is equals to the PD across a voltmeter plus the PD across the internal resistance, right? But because the PD across your internal resistance here is almost zero, so therefore the voltmeter gives you the EMF. So that's the actual reason. Understand? So it's because the voltage here is almost zero. Now then what we do now is we will connect this cell, okay, to another resistor. So I should shrink this a bit. Okay, so now the idea is, now I will take the same cell with the internal resistance, I will connect it to an external resistor, R. Alright, and this you can still connect a voltmeter across. Alright, you connect it like this. So what will happen is, the voltmeter, what will it show you now? If you think about it, right, there are actually two loops. There's one loop here and there's another loop here, right? Of course, there's a third loop here, which we're not going to care about that. So the first loop here, let's talk about the conservation of energy. So once again, in this loop, the EMF will equal sum of PD. And in this loop, the net EMF, the EMF must also equal the sum of PD. So if we do the equation, which is this, E, which is for the top loop, so E equals to PD across the external resistance plus PD across internal resistance. Agree? So now we do the equation for the bottom loop. So once again, we have the EMF E equals to the PD across the voltmeter plus PD across the internal resistance. Now you will notice that because we are referring to the same cell, so these two EMF must be the same, right? We are referring to the same internal resistance, so this is the same, right? So therefore these two must be the same. So the voltmeter reading actually gives you the PD across your external resistor now. So the first case, the voltmeter gives you the EMF here, but second case, the voltmeter gives you the PD across this. So some people ask me, why different? Because this one, voltmeter is still connected across here, voltmeter is still connected across here. The only difference is this, right? But why doesn't it give you this? Actually, it still gives you the PD across this, because you think about it, remember all voltages in parallel must be the same. So this PD equals to this PD equals to this PD, right? Now, actually, this EMF was equal to this plus this one, because this is 0, so this gives you this right now. Now, if you look at this, these are all parallel, right? So, the voltmeter is connected to here and here. So, this side has the same potential. The voltmeter on this terminal connected to here and here. So, all three will have the same potential. So, therefore, the PD here, PD here, PD here is the same, right now. So, what happens here is like this. Why does the voltmeter show you the the PD here and not the PD? Actually, it's the PD here. I'll tell you why. Now, when the current flows through this resistance, right, the potential will drop. Why? Because it loses energy right now. So the voltmeter shows you how much energy it loses per unit charge here. But at the same time, the voltmeter also shows you across here, but there's a difference. Now remember, when it passes through the cell, it gains or loses energy? Gains. When it passes through the internal resistance? Yes. So that means from here, this EMF and this PD are opposite signs. This is a gain and this is a loss. Example. Now, let's say this is 1.5 volt cell and the PD across here is 0.3 volts. So what will the voltmeter show you? That means first it increased by 1.5, then it drops by 0.3. So overall, it only increased by 1.2, which is also this PD, which is 1.2. So actually, it is not to say it's not measuring here. It is measuring here, but the PD here is significant already. Last time, the PD here was almost 0. Now the PD here is no longer 0. You know why? The current the current cannot flow here, but the current can flow here. So when current flows here, the current that flows here will also pass through your internal resistance and causes PD here. So when you measure across here, it will be EMF minus this PD. Here it could have happened, except that here the current is almost 0. That's why this equals to this. Okay? So now, after all this story, what is the conclusion? The conclusion is very simple. If you connect a cell with internal resistance to a voltmeter, you will assume the voltmeter's reading is actually exactly the EMF. But once your cell with internal resistance connected to external resistor, the voltmeter which is connected across the cell is actually giving the PD across the external resistance, which is also this EMF minus this PD. That's all you need to know. Why? Because when we want to calculate the internal resistance, we will fall back to this equation now. So the equation is E equals to VR plus VR. Okay? Now this is your first voltmeter reading. This is your second voltmeter reading. So can you find this? So once you know this is equals to I times small r. So find out the current and you will be able to find your internal resistance. So usually how do we find the current? If we know the PD across this, we take the PD divided by this resistance, you get the current here, which is also the current here. That's all. Okay?